Welcome to EDUNGURU students. In today's session, we will be discussing about polarization of light. We are aware that light is an electromagnetic wave, right? Now, the expression for a wave is given as E is equal to E naught sine omega t minus kx plus delta, right? This is the expression for a wave. Now, this E is representing the electric field, right? Now, we say that when the light propagates in a medium, right, this electric field wave, the electric field of the light wave is perpendicular to the direction of propagation of light. This electric field E vector is perpendicular to the direction of propagation of light. Right? So, E vector is perpendicular to the direction of propagation of light. So, suppose I say that if the direction of propagation is x-axis, let me draw this axis first. If the direction of propagation is x-axis, this E vector will be in the yz plane, right? This is the yz plane. So, this is representing the direction of propagation of light, and the E vector on this plane is perpendicular to the direction of propagation. So, this field E vector will have two components, one along the y-axis and one along the z-axis. Now, this perpendicular direction or this electric field vector can have infinite direction. Though it is lying on the yz plane, since the light is propagating along x-axis, this electric field vector can be along any direction on the xy plane, because it only has to be perpendicular to the direction of propagation of light, right? So, if at a given point on the medium, the direction of electric field is always constant, or if the electric field is always along a fixed direction at a given point, then we say that the light is linearly polarized. I repeat, if the direction of electric field at a given point on the xy plane is always along the same direction, then the light is linearly polarized light, right? So, I will write it here. If the electric field at a point always remains parallel to a fixed direction, as time passes, the light is called a linearly polarized light. Along that direction. Right. The plane containing the direction of propagation and electric field is called the plane of polarization. Right. Now, can anybody tell me how light is produced? Anybody in the class? Okay, I'll explain it to you. See, light is produced by oscillating atoms, right? It is produced by atoms. And every atom will produce a light in a specific direction, right? So there are large number of atoms. So every atom will produce light in their own direction. The direction of resultant electric field will always be varying, and it will be varying very rapidly, right? So in this case, what is happening is the direction of resultant electric field is varying very rapidly. Its magnitude may also vary, right? So this type of light is called unpolarized light. This type of light is called unpolarized light. Now, we are aware that if the light is moving along x-axis, or if the light is propagating along x-axis, the components of electric field will be along y-axis and the z-axis. Suppose if I say, suppose an unpolarized light travels along positive x-axis, the field will be on the yz plane, the resultant electric field will be on the yz plane, and we can give the components as Ey and Ez. Ey is the component along y-axis, component along y-axis, and Ez is component along z-axis. Since resultant field, this is the resultant of Ey and Ez, right? Since resultant field Er is changing its direction, randomly. Since Er is changing its direction randomly, we can write the expression, or we can take this fact into consideration by writing the components as Ey as E1 sine omega t minus kx, and Ez is equal to E2 sine omega t minus kx plus phi. Now here what we are doing is we are taking this phase constant. This phase constant is a variable phase constant, right? It is changing with time. So you can see here that both Ez is phi ahead of Ey, but this phase is changing with time. So at some point in time it may be behind, it may be lagging Ey, right? So if this expression, these two expressions are taking the fact into consideration that the resultant electric field is ever changing on the yz plane, right? It is changing in direction, it may change in magnitude as well. So these are the components of the resultant electric field. Now if I say, if the resultant electric field Er makes an angle theta with y-axis, then I'll draw this first. If this is the resultant electric field Er, this is y-axis and this is z-axis, right? So along this direction, there will be this EY component, and along this direction, there will be this EZ component. So if this angle is theta, then tan theta is equal to Ez upon Ey, right? Now we have tan theta is equal to Ez upon Ey, and this is equal to E2 sine omega t minus kx plus phi divided by E1 sine omega t minus kx. This is tan theta is equal to E2 sine of omega t minus kx plus phi upon E1 sine omega t minus kx, right? Now if, since phi changes with time, since phi changes rapidly with time, therefore theta also changes with time, right? And therefore we can say that the light is unpolarized, right? Because the resultant field is continuously changing in magnitude as well as in direction. Now let's take certain cases. First case is if phi is equal to 0, then tan theta, which is equal to E2 sine omega t minus kx upon E1 sine omega t minus kx. Now this cancels out, right? So we get tan theta is equal to, E2 by E1. Now this E2 and E1 were the maximum amplitudes of the electric field along z-axis and along y-axis, right? So these are constants. So this gives us that tan theta is a constant. Tan theta is a constant, right? Since tan theta is constant, therefore we can say that the resultant field has a specific direction at that particular point, right? So we say that the light is linearly polarized. Since tan theta is equal to E2 by E1 is a constant, we can say that the light is linearly polarized. Let's take the second case. When phi is equal to pi, so tan theta now becomes how much? Tan theta becomes E2 sine omega t minus kx plus pi upon E1 sine omega t minus kx, and this is equal to minus E2 by E1. Again, this is a constant. So here also we can say that the light is linearly polarized. Let's take case 3, where phi is equal to pi by 2. We have tan theta is equal to E2 sine omega t minus kx plus pi by 2 upon E1 sine omega t minus kx. Now this is equal to E2 by E1 cot omega t minus kx, right? This is tan theta. or we can write it as E2 upon E1 tan of pi by 2 minus omega t minus kx, right? This is tan theta. Now, if E1 is equal to E2, then theta is equal to pi by 2 minus omega t minus kx. So, theta is equal to pi by 2 minus omega t minus kx, right? And you can see here that as t changes, or let me write it like this, we'll be able to, theta is equal to pi by 2 plus kx minus omega t. So, theta is equal to pi by 2 plus kx minus omega t. Now, you can see here that as t changes, as time t changes, theta is decreasing, right? So, we can say that theta is changing with time as time t changes, right? So, the resultant field will be moving in the angle of resultant field is changing with time. What about the magnitude of the resultant field? Its ER is equal to, or ER square is equal to E1 square sine square omega t minus kx plus E2 square cos square omega t minus kx. Why this cos? Because it's sine of omega t minus kx plus pi by 2 is cos of omega t minus kx, right? So, since E1 is equal to E2, ER square is equal to E1 square, or ER square is equal to either E1 square or E2 square. So, you can see that the resultant field has a fixed amplitude, but it is changing its direction with time t. So, what we can see from this particular discussion is, you can see that theta is changing with time t and the amplitude of the resultant field is constant, right? What we can see from this discussion is theta is changing with time t and the amplitude of the resultant field is a constant, right? Now, the tip of this resultant field, since the variation is in theta, right? Suppose I say that this is the tip of the field and the theta is changing, right? So, if I say this is theta, then this theta is continuously changing with time. This theta is continuously changing with time, but the tip is rotating, the tip is lying on this circle only, right? The tip of the electric field vector is lying on this circle only. So, we say that the light is circularly polarized. So, we say that the light is circularly polarized, right? So, this is an example of circularly polarized light. So, this is an example of circularly polarized light, right? Now, let us take another case. In this case, theta is pi by 2 minus omega t minus kx, right? This is theta. Again, it is changing with time t, but here E1 is not equal to E2. E1 is not equal to E2. Now, since this is the case, since E1 is not equal to E2, since E1 is not equal to E2, the tip of the field will move in an elliptical path. and this type of light is known as elliptically polarized light. This type of light is known as elliptically polarized light. So in this session, we have discussed about the plane polarized light, unpolarized light. We saw different cases when can the light be circularly polarized, when it can be elliptically polarized, right? In the next session, we will be discussing about Polaroids, which are the substances or materials which are used to obtain polarized lights. We will discuss about law of Malus, and we will also discuss about Brewster's law. Till then, thank you very much. See you in the next session. Goodbye. In this session, we have discussed about polarization of light. We have seen the conditions for which the light can be polarized. So before moving to the next session, please answer these three simple questions. Question number 1. If the electric field at a point always remains parallel to a fixed direction as the time passes, the light is called option A, linearly polarized along that direction, option B, plane polarized along that direction, option C, both linearly and plane polarized, option D, none of these. Question number 2. If the phase difference between electric field vector along y-axis and along z-axis is pi by 2 and the amplitude of electric fields are equal, then the light is option A, linearly polarized, option B, elliptically polarized, option C, circularly polarized, option D, none of these. Question number 3. If the phase difference between the electric field vectors along y and z axis is equal to pi by 2, but E1 is not equal to E2, that is, the amplitudes of the electric fields are not equal, then the light wave is option A, linearly polarized, option B, circularly polarized, option C, elliptically polarized, option D, none of these.